Victor Robles can talk to us about fuzzy and self-interacting dark.
Thank you, Mike. So I'll talk about some out-of-box physics. So first of all, well, for those that don't know me, I'm Victor Robles. I'm a postdoc at UC Irvine, and I'm collaborating with a bunch of people in this room. And others that have left, and some others are somewhere else. So, so first of all, this is This is our picture of the universe. Can you hear me? Okay. We know that there is baryons, dark matter, dark energy. So this is roughly what our universe looks like. So we have some understanding of the baryons. So we know what the fundamental particles of those are. So it's really interesting because we know a lot of properties from of the baryons because we can actually observe them. But unfortunately, there is 24% of dark matter that we don't know what it is. And in fact, there's a very large regime of energies or particle mass where people have come up with models to describe this component. And the thing here is that most of the results and most of the simulations and all the most of the effort has focused on the cold dark matter model. But so there are a lot of searches now going on and a lot of money invested in experiments trying to look for WIMPs. And also now people are starting to look at the low mass end, which, you know, roughly like action-like particles in this sort of experiments like the action dark matter experiment. So here's a very cartoonish way of like what is the modern theoretical astrophysics process. So basically, you come up with some, well, observers just give us a certain observation of a quantity. Then you come up with certain model. And then if you have some understanding of this, then you can run a simulation, dark matter simulation. And then you can ask yourself the question whether you have good agreement or not. And if the question basically has a negative answer, then people are now starting to rely on hydro simulations and then ask the same question. And if we still have like a negative answer, then most of the people are now trying to figure, you know, only this step. So there might be something wrong with astrophysics, and that's a very interesting thing. But today I'm going to talk about something that maybe it's not here, but lies on the fact that we're actually getting I wouldn't say the wrong model, but, you know, kind of like explore what will happen if you change this. And then you redo the same process. So first of all, here's the observation. So we know that there's a Milky Way, there's Andromeda, and we have a bunch of satellite galaxies around them. And so much of these galaxies, the dwarf galaxies, are sort of believed to be dark matter dominated. They have very high mass light ratios. So these are very interesting candidates to look for potential differences in the dark matter models. So here's just a closer look to what local group galaxies look like. So fortunately, the light's not very good here. So, but, you know, observations are really hard to make. So there's this question, especially in dwarf galaxies, where these have cause or cores, which is related to what Joel said before. And that I'm not sure if these galaxies have cores or not. But as I said before, the process is to run a simulation, which is one of the suites that Alejandro sort of described is this Alex Fitz et al., in which they basically run a couple of simulations of a fixed halo mass, sort of to start exploring, you know, the compatibility of our understanding of dark matter with observations. And here's just the dark matter distribution of two of these galaxies. So this is a galaxy that forms about 10 to the 5 solar masses. And stars, and this is the one that forms 10 to the 7. So you can sort of see that there is a difference in the inner distribution of dark matter. So let's just quantify that a little bit. And these are 3 of these simulations. You can see that, so you have galaxies that form about 10 to the 5 stars in the galaxy, and then you can see that they've retained the cusp. So here the dark lines are the hydro simulations, and the gray lines are the dark matter only ones. And you can see that there is a very clear trend in as you increase the stellar mass, then you start forming cores, and somewhere in between you have these profiles that go, you know, in between like cusp and a core. So what's interesting from these simulations is that first of all you can see this trend that core formation in CDM in hydro simulations is very strongly depending on the stellar mass that's formed the galaxy. So another interesting thing is that we do have some observations where we can, or at least galaxies where we can start testing these models. So if we take a look or a closer look to the inner slopes of these galaxies, so this is not particular fire, and Chris and Ariana will talk. Well, Chris talked yesterday. So we sort of see that this happens in different implementations of feedback and astrophysics within the CDM model. So we can see that there is a very sharp trend or a threshold, if you want to call it somehow, around the scale of classical dwarf galaxies, in which basically the CDM predicts a sharp decline to a cost for small galaxies. And it turns out like these sort of threshold lies around 3 × 10⁶ solar masses, and that's roughly where the supernova energy is not really enough to start forming cores. So this is very interesting because this is a clear prediction of CDM, and if we're actually going to try to search for differences of these dark matter models, then this is a very interesting regime to do that. So for instance, so what happens if you add self-interactions to the dark matter? So, well, these models have been exploring different papers now. So essentially the idea is, you have some scattering rate of these dark matter particles, and it roughly depends on, the dark matter, the local dark matter density, the cross section over the particle mass, and this and the velocity, or like the Brownian square velocity of particles. And what's interesting is that once you reach the scattering rate, in which you have like roughly around one interaction per Hubble time, then you start getting some differences with respect to CDM. So here, Albert have explored this regime in dwarf galaxies, and for different cross sections, he's seeing like we're sort of quantifying the core sizes of these for different cross sections. So for the rest of the talk, I'm going to concentrate on the 1 cm² per gram, which is still viable, or at least possible by other cluster constraints and so on. So these are dark matter simulations, and we're going to go one step forward and then add the astrophysics using fire. So I'm not going to talk about fire because Phil actually talked a lot about it. So here are the results. Basically, these are simulations with fire 2 and the self-interacting dark matter as implemented by Rocha et al. So these are the 3 galaxies that I showed before, but now we have those SIDM on top of that. So the dashed lines are SIDM, and the solid lines are CDM. So first of all, I would like you to concentrate on the thick line. So the thick line is the result from the hydro simulations, both CDM and SIDM. And you can see like there is this very close very small scatter from like the dashed line, the SIDM density profile, which is the hydro simulation, and the thin lines, I forgot to say that. So the thin lines are the dark matter only simulation. So you can see there's very small scatter with respect to the dark matter only simulation in SIDM, whereas you can recover, what basically I showed before, you can see this strong dependence on the stellar mass for CDM to produce cores. So what's interesting about this is that we can sort of quantify these differences, and about roughly the High-mass radius of the galaxy. So this is a 3D High-mass radius. So you can see, you can compare those SIDM profile to, let's say, the CDM profile. So think of this as comparing, the SIDM profile to a cost. And you can see that there are already differences about like High-mass radius, and they become even larger as you go to a smaller radii. And in fact, you already have like a 25 to 50% difference about like High-mass radius, which is in principle observable. So so then if we quantify a little bit more the inner slopes, which I just showed that there might be some predictions of CDM. So you can again sort of see like the field points are the hydro simulations, and you can see this sharp decline as you go to smaller stellar masses. Whereas in SIDM, we have a very small scatter, and you can see that the effect of fire is actually very small. So compared to the dark matter only one. So this is really a very nice result, because what this is telling you is that SIDM is fireproof. And what that means is that dwarf galaxies in SIDM are actually much less sensitive to feedback, which makes it really a very predictive model. So if we come back to this plot, which is showing you just the inner slopes and versus the stellar mass, So here are just some of the observations. So you can see the things and little things, dwarf galaxies. So of course the error bars are large. So this is just a vicinity profile from the anyhow simulations. So what you get, or the results from the vicinity simulation. So here's the 4 galaxies that I showed for the CDM. So you can see this sharp decline. And this will be the same simulation as IDM. And here you can see that there is very sharp, very important difference where you can start testing this. And it's interesting because they lie around the range where you have the classical Milky Way dwarfs. So again, like we in principle have some observations where we can start exploring these differences. So just extrapolating the line, and then people might actually say, well, it seems like you're also going to a cost. So that might be the case. We don't really know where this lies, so that's the importance of running even more simulations at the low mass end. So the reason of that is just because the scattering rate basically becomes about the Hubble time for even smaller radii, which comes basically from the fact that the densities are becoming smaller. So if you take a look at the global properties, so you can sort of see that these galaxies like SIDM and CDM roughly lie about the same relation or stellar mass or half mass relation. But if you take a closer look, at least for these galaxies, you can see that basically this is the CDM galaxy, this is the SIDM galaxy, same initial conditions, same fire physics. So the only thing that happens is that you're actually producing twice as many stars for the SIDM galaxy. So we can't really have some implications for this in the stellar halo mass stellar halo mass relation. Of course, this is just one point, so I don't want to claim anything at this point. But if there is actually a difference, so it will be roughly in this sense. So you will have, about like 10 to the 10 solar masses. Then SIDM will producing actually larger number of stars in the same galaxy. So that actually transfers into this halo mass function or the galaxy mass function to a steep slope here. So that just bear in mind that that's very preliminary. So one point can actually just be part of the scatter. So so we hear from. So here, yeah. So basically, if this is true, and galaxies in SIDM are actually producing more stars in the same halo masses, so having galaxies are more luminous, or in terms of the stellar mass. So that will imply that you are preferentially in this high mass slope. Yeah. So this will be the self-interacting. Well, I mean, there is large scatter, so that will be what these error bars are. So if you believe the medium, the media, well, it will be kind of like this smaller. So it will be somewhere in between this. Yeah. So we heard from Phil that galaxy formation basically relates different scales. So I don't really have a lot of time, so I'm just gonna try to flash this very quickly. And so what happens if we actually take this to a very streamed regime in which we actually go to very small scales. So this is the other model that I've been working on, which is called the ultralight scalar field, which basically assumes that the dark matter particle is very light. So it's about like 10 to the minus 22 EVs, which there are reasons to believe why this number is preferential, so I cannot talk about that now, but you can ask me later. And essentially, this mass, what we produce is a very large de Broglie wavelength, so we'll have some quantum properties of galactic scales. So, so this is just for those that don't really know what Bose-Einstein condensate looks like. So this is not the first time that the quantum physics has some microscopic implications. So you can see here. So this is just a Bose-Einstein condensate in the lab. So you have a cloud, so you have a gas and you cool it down, and then at some point you see this transition where most of the particles just go to a single quantum state. So this is my representation of what will be sort of in the universe. So you have a galaxy and there might be some underlying dark matter that has some quantum properties that will be, sort of like wiggling around. So we sort of explored that idea with this, it's just like 40 seconds. So if Mike is not going to kill me, I'm just going to take some of 40 seconds of your time to actually show you. So this is a very simplistic simulation. So what we did here was to start a simulation with the typical solution of this dark matter model, in which you have a core, which is basically called a solitonic profile or a solitonic core, which is characteristic of all a characteristic solution of the ground state of this system of equations. So we started with this bunch of, say, halos or dark matter halos, and then we started merging them. So we ran out 100 simulations of this with different configurations, and we sort of normalized the density profiles here. And we show here is that basically all of them have this sort of universal flat slopes or solitonic cores with an FW-like tail. So so here I'm just going to try to wrap up. So basically what we have here is the CDM, this is the SIDM, and if you believe these results that we are getting, then this will be SFDM or back dark matter. So there is a very clear distinction between these three models and in general that about dark matter that we could potentially test. So so I'm telling you that this is at least observable. And in particular, if we get like even deeper observations of ultra-faint dwarfs and so on, then maybe we can start looking at these differences. So just 3 slides. So this is work that I'm doing with Philip Knox. So it's a postdoc now at Princeton. So this is the cosmological run with back dark matter. And this is the cosmological run, same initial condition for the CDM. And you can start seeing already differences in larger scales. So these are independent tests to the ones I mentioned in dwarfs. So this is work in progress. So I'm not going to talk about much about this, but I just want to tell you that there are potentially interesting differences. So first of all, if you look at these objects, then they sort of look like this. This is the projected density. You can see there's the solitonic core here in the center and some sort of turbulent medium here, or like dark matter turbulence, if you want to call it. And it's interesting because there are some galaxies in which we potentially could test this. So like this is the H1 gas that we heard in the previous talk. So maybe we can start comparing these two things, and we actually may get some interesting results. There's another thing that is related to the filaments, and we heard yesterday from Clotilde's talk. So that there is an importance in terms of like how close the galaxies are to the filaments and so on. So this might be also like another test that we could actually start exploring. So sort of like the number of galaxies or some effects like the shear and morphology, etc. So finally, I just want to tell you some preliminary work that we're doing. So this is at redshift 6. So this is the density profile coming from the back dark matter, and this will be the lambda CDM and FW panel. You can see that even at high redshift, you start getting denser systems, so denser galaxies, or well, halos, right? Say. So these might have implications related to the local group, some potential features like rings, and presumably even like early bulge formation. So finally, I just want to conclude with this, because Mike is looking, he's giving me the evil eye. So, so just finally, I just want to say that dwarf galaxies are very interesting, and they can actually offer independent tests to what the dark matter nature is. And so comparing CDM and SIDM with fire, what we got is at least looking at the inner slopes, we have a very clear prediction where we can test these models. And well, again, if you consider the back dark matter model, we have a universal profile. And then we also have, you know, really inner flat slopes at the very center of the halos. So, well, here's just like some upcoming work, and now I guess I'll finish that. I'll finish there. Yeah. Thank you.
Yes.
So a really quick technical question. You use the stacking parameter.
Oh, God.
Use the parameter for SIDM, which is like 0.1 per giga or something.
I use one. Yeah, I said it. Yeah.
So how consistent is that with the current observation?
With the what?
How consistent is that from the observation from some dark matter?
So that is still consistent in terms of the searches. So the problem with the, I guess was that your question? Like how consistent is that with particle physics, or? Yeah. So yeah, I mean, so the problem with the searches is that that's still consistent, right? So that's the short answer. And sort of not short answer is that there are some caveats there, right? Because we don't really know where to look for it. So that's kind of like why these sort of independent tests are important. Yeah.
One final question.
Regarding your question that it doesn't only use the solid, basically a little bit like all dark matters and basically cuts it to the small scale structure.
It does cut a small scale structure because of the small scale, but it's the mechanism is different from warm dark matter. Right.
The numbers you quote, you have to quote from the center mass. Is still consistent with historical structure?
So there are some words that are basically doing that, and they're still consistent as far as I know. There are some words that are quoted like a slightly larger value, but those are basically relying on, yeah, like at some of these high redshift observations, which are like just like 1 or 2 points. So it's kind of still, you know, under debate.
What's the shape of your system?
They're round.
That's wrong. That's inconsistent.
But only in the very center of the galaxy. It's like 200 to 500 parsecs. What?
What about the local dwarfs?
So this is dark matters that, yeah. So
Dwarfs are not round. No, you don't know what the shape of dark matter is.
yeah, so
Talking about the shape of the stars. Stars are flattened.
yeah, so what I was talking about here is just like dark matter. So Alejandro was more on the stars. So that's a very good question. I actually had to cut those slides, but we're actually taking a look at those access ratios for dark matter and stars. But yeah.
All right. Let's thank Victor again.